Okay, so far in Chapter 5, we started with derivatives and antiderivatives of logs, right? I mean, basically, that's what we were working with was logs. And then we moved into 5.3, this sort of idea of inverse functions, which didn't really have a lot of calculus in it. We saw a few kind of odd sort of things in there, but mostly it was college algebra. And we did that because of the relationship that log functions have with exponential functions, and we're going to talk about exponential functions today, okay? So in particular, we're going to talk about doing derivatives and antiderivatives, or derivative differentiation and integration with exponentials. And this is the best rule ever. So if you've seen the derivative or the antiderivative for exponentials, this is the one you never forget, okay? All right, so this is where we came from. We talked about the inverse function last time. The inverse function of this is called the natural exponential function. Let me get a darker color. It's denoted by f inverse, right, because that's how we denote inverses of x, and it's equal to e to the x. That is y equals e to the x if and only if x equals the natural log of y. And I believe that I pointed this out last time to you guys. You can correct me if I didn't. But natural log of x, when you first encounter it from a college algebra point of view, you've already encountered something called a log. And we talk about the fact that this has a base of e. And so ln x means log base e of x. So you see that e, and it almost looks like it's an e with an exponent already of x, which that's not what's going on. But it kind of has that sort of feel to it. And that is actually its exponential function is e to the x. Its inverse function is e to the x. Exponential properties. So you should know these. You've encountered these so many times they should be like knowing the back of your hand. All right, the first exponential property is a to the m times a to the n. What do you do with those exponents? You add them. And very, very similar to that, if you have division of exponentials of the same base, a to the m divided by a to the n, what do you do with the exponents? You subtract. Another one that's often confused with number one is if you have an exponent, or sorry, an exponential raised to an exponent. Notice that is not the same as the first one, right? This one ends up multiplying the exponents together. Now, Emily tried to do this earlier today with me, but it wasn't quite what she's seeing now or you're seeing now. If you have two values that are multiplied together with an exponent on the outside, then you can distribute that exponent through. That doesn't work for everything, right? It matters that this is multiplication inside that allows us to do this. So this is a to the m and b to the m. And it works for multiplication. It also works for division. A to the m, that's an m, over b to the m. Notice there's not a rule that says what happens when it's addition or subtraction, because there is not a closed rule for every exponent when there's addition or subtraction. You don't just get to distribute it through. And the last one, which is sometimes helpful, has to do with the negative exponents that you encountered earlier, Cameron. So if you had a negative exponent with this.
I thought there's supposed to be an m after the quotation.
There should be over there, yes. I got carried away. Thank you. If you have a negative m as an exponent, you flip the fraction because it's the negative, right? So this is b over m, b over a. And then the exponent becomes positive, which means you could also write it as b to the m over a to the m. Either of those forms, depending on what you need. The first thing we're going to remind ourselves and look at is how one goes about solving both exponential and some logarithmic equations when we're dealing with these. So taking a look at this first example, we have an equation and it has an exponential in it. Very much like when you have any variable in an equation, when you're solving for it, you want to get the variable part alone. So what am I going to do first?
Take the 6 over to the 8.
Okay, I'm going to add the 6, right? So this is 3 e to the x equals 14. Then what? I would divide by 3 next. So this is e to the x equals 14 thirds. All right, so remember what it said, that the way that we can change exponentials is with logs, just the way that the logs and the exponentials were. The very first slide that we filled in sort of the gaps on, this actually can be changed by changing it into a log function. Now, there's lots of ways to sort of visualize that. I'll show you one of them. One of them is to, in other words, take the natural log of both sides. So if you take it from this perspective, this natural log here and this e has a log property involved. This x can come out to the front because it's an exponent, it becomes a coefficient. And then one of our properties before was the natural log of e, and what was the natural log of e equal to? 1. So this whole expression on the left-hand side becomes, not 1,
Or
x. Okay, so again, what we did is that this x comes out in front. I have natural log of e here, and natural log of e is 1. Okay, so everything on the left becomes x. And if you grab your calculator, it will give you a decimal approximation for the natural log of 4 thirds. Make sure the 4 thirds is in parentheses. Your calculators will probably force that, but in case it doesn't. And it says accurate to 3 decimals. So what do you get for x?
I was 14.
Oh, I lost my 1. You're right, it is. Thanks, Dylan. There's a 1 there. All right, so what's the approximation for natural log of 14 thirds? 1.5. What was it, Hannah? Good. And we talked about this last time, I think, or the time before. We do want all 3 decimals represented, even if the last one's a 0. Okay. Any questions on that one? Okay, let's try another one. Now, this next one is actually going to start as a log. And just like on the last one, the goal is to get the exponential part alone. So again, there's several ways to do this. I'm going to show you just one of my favorites. My favorite is to rewrite this, or to think about it anyway, as log base e of 4x equals 1. And if we think about it from that perspective, I like to do this. I'm a very visual person. So I had a fellow teacher, I guess you would say, who was teaching once, and they called this a scorpion tail. And if you've seen scorpions before, this would be the visual. Kendra's just cringing back here. This is the visual imagery of what their tail would look like. Okay, so it curls back around on top of it. The way that this does is you start with the base, so you circle the base. My base is e, so I can rewrite this with a base of an exponential as e. If I follow my circle around, it takes me to the other side of the equation. That other side of the equation, the number 1, becomes the exponent on my base. And then it equals where the arrow is landing, the 4x. That's not the only way to do this problem, but it is one way to do it. Okay? And then I'm nearly done. E to the 1 is just e, and your calculators will deal with that okay. And then I need to have the x alone, which means I need to do what? Do I need to jump up and down? No. What do I need to do? Oh, I need to divide by 4. I do. Okay, that's good. I didn't really feel like jumping. I'm kind of already hot. All right, so this is x equals, or at least x is approximately equal. It doesn't matter if you choose the approximation, but I'm supposed to, again, have 3 decimal places because the direction said so. So what is e divided by 4 in your calculator? And your calculator may force you to put a 1 in, like this. Sometimes it'll even, depending on the version you have, will even force it to have a parenthesis around it. whatever it is, do that and then divide the whole thing by 4. So make sure you're not dividing the 1 by 4, but you're dividing the e by 4. What do you get? Syntax error. That's not good. You shouldn't be getting a syntax error.
0.7 or 0.67, or I guess it would be 0.680.
Yes. 0.680 is correct. Okay. Did everybody's calculator finally cooperate to give him that? Okay, great. So you've seen half of this graph before. You've seen the lower half down here. This lower half of the graph right here was the graph of ln x. Do you recognize it? And we talked in the last section about graphing inverses. And we talked about imagining that there was a line cutting through the middle here. I'm going to draw it as best I can. Something like this. That's my line y equal x. And then if we sort of folded the image upon that line, y equal x, we would have the inverse. And we do. The inverse up here is the line, or sorry, the curve y equals e to the x. So that's the graph I'm actually talking about here where it says graph features. I'm talking about that last one that I kind of sketched over, y equals e to the x. So notice a few features. The first one there is that it has a y-intercept at 0, 1. Right here, right? It does not cross the x-axis. In fact, on the left-hand side, you'll notice it's getting ever so close to the x-axis, but it's not actually touching it, which is what's creating that horizontal asymptote at y equals 0, namely the x-axis. It's increasing without bounds. That's this right-hand edge. It goes up forever. And that notation, if you'll remember from Calculus 1, is that the limit as x goes to infinity of e to the x, it would be infinity. It doesn't ever actually level off. It increases without bound. What's the domain for this guy? What x values do you see or would be represented by this graph? Very good. The domain is everything. From a graphical perspective, the arrows on the edges of this thing indicate that, right? This arrow indicates that I can go left forever, and that arrow indicates I'm going up and right forever. So all of my x values are represented. From the equation itself, sort of an analytical point of view right here, you could think about e to the x. What values can x take on? And I can plug in anything for x. Your calculator won't give you a syntax error either. So you can put x as positive, x as negative. You could put a square root in there. You could, whatever. X can be anything you'd like. The range, however, has some limitations. What's my range for this guy?
0.
Yes, and I can't actually equal 0, right? So remember, range is my y value, so I'm going sort of from the bottom of the graph up. And this graph does not have anything beneath the x-axis, right? So that's 0. That's the lower bound for it. It does have a lower bound. And then it goes up forever. So I have an infinity as my upper bound. It's continuous. Again, we talked about that just means I can draw it without lifting my pencil, sort of conceptual idea. It's 1 to 1. Remember, 1 to 1 means it passes the horizontal line test. If I draw horizontal lines through this puppy everywhere, it crosses 1 time. Or not at all if the horizontal line is beneath the x-axis, right? And that's okay. And this one's concave up, which is interesting because its inverse is concave down, right? All right. We did this when we did graphs for, did you guys get all that? Very good. Okay. We did this transformations idea and graphed a little bit when we did logarithmic graphs, and we're going to do them for exponential graphs as well. I want you to recall transformations, and the general equation that we're going to be looking at when we're talking about it is an exponential. Looks something like this. I think you've got it written on your page. So we're going to talk about what the A, B, C, and D do to the graph, but I'm actually not going to do it in the order that I just listed it. So let's start with D. What does D do to this graph?
Moves it up or down?
Correct. So this is a shift vertically. I'm going to use your first words. Up. When is it a shift up? It's when D is positive. So when D is greater than 0, it shifts it up. And it's a shift down when D is negative. So we'll just go backwards. What about C? If adding a value to the outside shifts it up and down, what does adding a value to the inside? Notice you have an inside here. It's right here. It's inside with x. So what will happen if you add a value inside with x? That's what we just did. It was vertically.
It's going to
Left or right, horizontally, right? It's affecting the x value, and x value is a left and right movement. Okay? So this one is a shift left or right. So when is it a shift left?
When it's positive.
Yes, it shifts it left when C is positive, and it shifts it right when C is negative. It's backwards inside. Just for fun, we're going to go out of order again. Let's go back up to A. Why not? I am. I'm trying to confuse you today. All right, A out in front. The A out in front affects the Y value. It's not directly next to the X, in other words, right? So it's affecting the whole graph. So what will this do? What will happen? A and B do the same kind of thing. What do they do to a graph?
just want to stretch it.
They do some kind of stretching or shrinking, right? They stretch it out of shape. They don't actually pick it up and move it. The addition or the subtraction, depending on if C or D is positive or negative, is a shift. It moves it around. So I can just kind of go like this, and my hand didn't change shape, right? But the A and the B, those actually change the shape of something. So we're going to do A first. The A is a vertical stretch or shrink. So I'm going to do the stretch first. It's a vertical stretch when the A is greater than 1. So what you want to imagine is sort of like a parabola, okay? It works for any graph, so I'm going to imagine something that's easy for you to picture. You've got a parabola. Imagine taking the ends of the parabola, the arrows that point upwards, and stretching it up. What's it make it look like? It actually makes it look taller and skinnier, right? Okay. So that's a vertical stretch, and that happens when you have an A value bigger than 1. And then you actually get a shrink or a compression when the A value is between 0 and 1. Okay, so imagine like an ice cream sandwich, right? And you take it, and what do? You squish it down, right? And it makes it look shorter and longer this way too, actually, yeah? But you squished it down like this. So you're thinking about numbers like 1/2 and 1/3 and 0.2 and whatever, okay? Notice that did not take care of what happens if it's negative. What happens when we have a negative on a graph? Yeah, it'll either flip it up and down or flip it left and right. So the negatives do flipping. They don't stretch or compress or anything. They just flip things around the axes, okay? B is a horizontal stretch. Or shrink. And just like I said when we did C, the value for C, everything works backwards of what happened on the other one. So when would I get a horizontal stretch?
It's between 0 and
Right. It's when the B value is between 0 and 1 that it actually horizontally stretches it. Okay? So again, imagine the horizontal stretch in the picture that I just had before. This is like taking that ice cream sandwich and pulling it apart like this. So imagine the tug of war with the rope, right? It compresses the size of the rope. And then you get a shrink when the B value is bigger than 1. Okay? So imagine, again, you're squishing it back together like this. That shrinks it horizontally. It may or may not make it taller vertically, but it shrinks it horizontally. All right?
it's negative inside the parentheses that just
Yeah, not inverse, but it flips it, right? So let me mark those since you guys have asked. Right here, if the a value is negative, this is a flip. How? Does it flip it up, down, or left, right?
It's going to be up, down.
Yes. An a value that's negative is a flip up or down. And then change colors. If this b value is negative, this one will be a flip left or right. And I'm not specifying which one it is because it depends on where the graph was to start with. It just turns it around. So if there's stuff on the left, it moves to the right, and if there's stuff on the right, it moves to the left. It just, oscillates the whole thing. It does like this, right? It turns it around, however it was from before. All right. So let's do some calculus, though. Oh, did you have a question, Emily?
Yeah, could you show like a graph of what the horizontal stretch would look like? Or the stretch or shrink, whichever one.
Yes, we can do one, sure. Let's do the difference between, let's just do an exponential since we're dealing with exponentials. So let's graph your regular graph y equal e to the x. I'll do it on the screen here in a minute. And we will graph y equal e to the 2x. Okay? And then we'll do y equal e to the 0.5x. We'll graph those three. All right, so we're going to take a look at some of the calculus going on here, and this is what I told you that you're going to be forever grateful that I told you this rule, forever and ever and ever. All right, so here's the deal. If you have a function, or have the function e to the x, then its derivative is e to the x. And it doesn't get any easier than that, right? He is the only derivative. He's the only function whose derivative is himself. Say it that way. So this is actually on your derivative sheet as well, if you want to fill in rule number, whatever we're on your derivative sheet. This was the next rule in the line of rules. And we're going to find some derivatives. Surprise. But this is adding on to a bunch of derivative rules like chain rules and product rules and quotient rules and things like that. So you're going to see some of them occurring in the midst of this. All right, so take a look at this one. We've got y equals x squared e to the negative x, right? So first of all, what kind of overarching rule is this? There is a power rule in it. What else? Multiplication. This is the product rule, right? And that's the overarching rule, is it's a product. So we're going to have to deal with the product. Inside of the product, there's going to be a power rule, and there's going to be a chain rule, and we've got this new e to the x rule involved as well. Okay? So first, let's do this. I have a feeling that you guys have been taught backwards of how I normally think about it. So what is the derivative of x squared? 2x. And then I rewrite the second piece just as it is. Correct? And then I put an addition sign, part of the product rule. And then I need the x squared rewritten just as it is. And now I've got the derivative of e to the negative x. Well, if this were just e to the x, what would its derivative be? E to the x. So that's my overall rule here. My overall rule is that when I say e to a power, its derivative is e to the power. The difference here is that